The ratio test is trying to detect how geometric a series is. Because we know exactly what geometric series do, right? Geometric series will converge as long as their ratio, their common ratio, is between positive and negative 1. The ratio test is an attempt to figure out to what extent a series looks like a geometric series if we go far enough toward infinity. So here's what I mean by that. And we'll go back to the sorting hat in a minute. Remember this series? N divided by 3 to the n, which Mathematica has sort of rewritten here. But this was a series we looked at as one of our first comparison test examples because it came up in a homework problem. And when we were trying to assess whether or not this series, n over 3 to the n starting at 1 going to infinity, converged or diverged, first of all, what did it turn out that this series did? Converge or diverge? When we applied the comparison test to it. This one converged, right, but in order to make that comparison, we ended up comparing not to something that looks exactly like it, but we had to lower that geometric factor in the denominator to 2. So we compared this to 1 over 2 to the n, using, again, the L'Hopital's comparison test, the limit comparison test. Right? So using the limit comparison test, we were able to show that this was a convergent series, but it was kind of messy, right? We tried one comparison to 1 over 3 to the n, and that comparison didn't work. So then we went and we tried another comparison. That comparison did work. But really, our hunch about this series was that this 3 to the n, down in the denominator, was responsible for the end behavior of the sequence. And the end behavior of the sequence, as n goes out to infinity, that's what determines whether the series built out of that sequence converges or diverges. In other words, our intuition about this series was that basically this series looks geometric. I'll put that in quotes. It's basically geometric. Because in the grand scheme of things, this 3 to the n is of a much higher order than the n in the numerator. And so the end behavior of this sequence is going to be governed by that 3 to the n, which lives up here, and not by that n, which lives down here. So the 3 to the n is wearing the pants in this relationship. And so basically this looks like a geometric series. That's our hunch. That's our intuition. And what the ratio test does for us is it makes that intuition precise. It tells us exactly in what sense we can say that a series is basically geometric, even if it's not exactly geometric. So here's the idea. So we're looking at the first few terms of this series over here. Maybe I'll even look at the first lesser terms. Let's just look at the first 5 or something like that. So here's the first 5 terms of this sequence. Now, how do we know, first of all, that this is not a geometric series? I'm going to rewrite these terms a little bit larger here. The first term was 1/3, the second term was 2/9, and the term after that was 1/9, and then 4 over 81. How can I prove to you, or how can you prove to yourself, or prove to somebody who's not taking our class that this is not a geometric series?
Common ratio.
Let's find the ratios. Right. So if I take the ratio of the second term to the first term, that's going to be 2/9 divided by 1/3. Reduce that out. I believe it's 2/3. And so the ratio between the first term and the second term is 2/3. What's the ratio between the third term and the second term? Yeah, it's a ratio of 2 going one way, or if we divide 1/9 divided by 2/9, it's 1/2. So immediately, we can say this is not a geometric series because why?
Not a common ratio.
Because the ratio is not common. I mean, there's a ratio, but the ratios between successive terms for a geometric series have to be the same. But these ratios are different. So right away, we can say this is not a geometric series, at least not exactly. But there might still be some value in looking at these ratios and continuing to look at these ratios as we go further and further out towards n equals infinity. The next ratio, 4 over 81 divided by 1 over 9, that's 4/9. And so if we keep track of these ratios, I call them R sub n. I'm going to keep track of those in a separate table here. The ratio of the second term to the first term was 2/3. The ratio of the third term to the second term was 1/2. The ratio of the fourth term to the third term was 4/9. And let's look at the behavior of those ratios as n tends out to infinity. This is a job that I'm going to ask Mathematica to do for us. So show me the ratios. Here they are, in decimal form anyway. Those are the first few of them. And if we decide that we want to look at more, and we do because we'd like n to tend out towards infinity, there we go. So here's the first 11 ratios. So can you tell me anything about what those ratios are doing? It looks like the ratios are, well, they're getting smaller, but they're not getting that much smaller every time. It looks like, especially looking at the graph where I've actually plotted the ratios out, it looks like the ratios are leveling off to something. And that something that those ratios level off to is what we call the asymptotic ratio of this series. And in our example, what does it look like? It's leveling off to point, at least as far as the first few terms that we're looking at here, we get approximately 0.36. Again, that's some pretty good evidence, right? But let's be analytical about it. Let's determine what this asymptotic common ratio is using, instead of numerical and graphical evidence, let's use the formula for A sub n. So what is the asymptotic ratio of this series? The first job is that we need to divide, again, the n plus first term in our series divided by the nth term. And really, we would need some absolute values here as well, except that we already have a positive series, so it doesn't matter whether we have them there or not. We're going to get the same answer. So I'll use the formula that we have for A sub n. Again, we can think of this as n over 3 to the n. It's the way that I'm used to seeing it better anyway. And so I'm going to have, in the numerator, n plus 1 divided by 3 to the n plus 1. And in the denominator, I'm going to have n divided by 3 to the n. So we have one of these nasty compound fractions again. Well, what do I get when I reduce that compound fraction out? I have a 3 to the n upstairs now, a 3 to the n plus 1 that remains downstairs. But then I also have an n plus 1 upstairs and an n downstairs. And what I like to do in these ratio examples is I like to take those factors that correspond to one another, and I like to keep them in their own fraction. So 3 to the n and 3 to the n plus 1 I'm going to keep here. N plus 1 and n, because they came from the same place, I'm going to keep them there. Just to organize the factors as much as we can. All right, but let's simplify this. N plus 1 divided by n, we don't need to simplify that too much. Let's leave that the way it is. But how can I simplify 3 to the n divided by 3 to the n plus 1? Yeah, I've got in the denominator one more power of 3 than I have in the numerator. So when the dust settles, I have 3 to the 1, and it lives in which part of the fraction? Downstairs. So 3 to the n divided by 3 to the n plus 1, we simplify to 1/3, and then I have n plus 1 over n. So this expression, if we plug in the different values for n, it should actually give us the values of these ratios that we see here in the table. So when n is equal to 1, for example, I get 1/3 times 1 plus 1 over 1. 1/3 times 2, that's 2/3. That's exactly our first common ratio. When n is equal to, 5, I get 1/3 times 6/5. That's 2/5, 0.4. That's what we see right there. So this formula that we just got for the ratio, the sequence of ratios, is giving us everything we see in the table right there. But ultimately, we don't care about the ratios individually. We care about them asymptotically. In other words, we care about what happens to these ratios as n goes out to infinity. So what should I do? I should, quote unquote, plug in infinity. And how do you plug in infinity in calculus? Take a limit. So what I need is the limit of these ratios, which are 1/3 times n plus 1 over n. That limit as n tends out to infinity. And that's the quantity that we call rho, the asymptotic ratio of this series. Well, what do I get when I take the limit of 1/3 times n plus 1 over n as n tends to infinity? First of all, what happens to this 1/3? Nothing. But what about n plus 1 over n? What does this tend to? Tends to 1. Everyone see why? L'Hopital, or perhaps just divide the numerator and denominator by n and take that limit. So the n plus 1 over n piece is tending to 1. And so my limit, my asymptotic common ratio, is equal to 1/3. So our prediction, by the way, based on the first 10 of these common ratios, it looked like it was about 0.36. Well, according to the calculus, we were pretty close. 1/3 is 0.3 repeating. So after the first 10 or 11 ratios, it had a little bit more settling down to do, and it eventually settles down upon 1/3. So that 1/3 here is the asymptotic common ratio of this series. Now, what does that mean? You all know the ultimate answer based on what you read and watched about the ratio test. But let me try to explain why. Just again, as a kind of a back-of-the-envelope idea. That this sequence looks kind of like, well, again, it starts out with these terms, 1/3 plus 2/9 plus 1/9 plus 4 over 81, etc. The first few terms don't look very geometric. But what the asymptotic ratio is telling us is that eventually, asymptotically, as we get far enough out in this series, it looks an awful lot like 1/3 to the 1 billionth plus 1/3 to the 1 billion and 1 plus, etc. In other words, way out in the tail, we get something that looks exactly like a geometric series. Well, exactly in quotes. It looks geometric. And this common ratio that we computed would be the ratio of the geometric series that this thing looks like. And we know exactly what ratios make geometric series converge. What are they? Ratios between 1 and -1, inclusive. So because our ratio here is less than 1, we conclude that our series should be convergent. Summation of n/3 to the n. So that's the power of the ratio test, is when we have a hunch that our series is basically geometric. In other words, when a geometric factor is wearing the pants in the relationship that is your sequence of terms, the ratio test is a good choice because it measures, if this were a geometric series, then what would its ratio be? And once we know what its ratio would be if it were geometric, we call it the asymptotic ratio, then the conclusion of the ratio test is the same as the conclusion for whether a geometric series converges. Is that ratio between -1 and 1? Or between 0 and 1 because we've taken just positive terms here? And if it is, then we get a convergent series. If it's not, if the ratio is bigger than 1, we get a divergent series. In particular, when the ratio is bigger than 1, rho. When rho is bigger than 1, actually the terms of our series are not going to go to 0. The terms of the series are going to blow up to infinity anyway. So if you're using the sorting hat in the way that we have the sorting hat laid out, probably getting that ratio to be bigger than 1 is something that wouldn't happen, because he would have already thrown away that series based on the divergence for dummies test. But the conclusion is still the same. If the ratio is bigger than 1, then the terms are blowing up to infinity, and so the series must definitely diverge, because in order to converge, the terms have to go to 0. So there's only one example of a common ratio that tells us nothing, and that's the common ratio rho equals 1. So we want to look at an example of that before you get into your groups today.